Welcome to the 21st lecture on digital simulation. In the previous lecture, we have seen how to do transient analysis of electric circuits. And in this video, we will see another technique using equivalent circuits to do transient analysis. And we have seen that the presence of capacitor and inductor in electric circuits necessitates this type of analysis. And in this video, we will see how to replace a capacitor by an equivalent circuit. And after getting the equivalent circuit, we can straight away write the equations. Similarly, we will see how to replace the inductance by an equivalent circuit, and from the equivalent circuit we will be able to directly write the transient analysis equations. So let us start with the capacitor. So suppose we have a capacitance connected between node P and node Q in a circuit, and all of us know that if the voltage across the terminals of the capacitor are denoted like this VC, and if the current flowing is IC, and these two quantities IC and VC are related by this equation, C into dVC by dt is equal to IC. And from our backward Euler technique, we can rewrite this equation as C into Vc of n plus 1 minus Vc n by h, where h is the step size, equal to IC n plus 1. So we know that Vc is nothing but Vp minus Vq from the figure. Voltage between node P and node Q is Vc. So Vc n plus 1 is nothing but Vp n plus 1 minus Vq n plus 1. Similarly, Vc n is nothing but Vpn minus Vqn. Okay. Now this quantity C by H, we can write it as Gc. Okay, so in the previous equation, I have replaced this quantity by Gc. So Gc into Vp n plus 1 minus Vq n plus 1 minus Vpn minus Vqn is equal to IC n plus 1. So that is written in the next page. So bracket is opened and Gc is multiplied. So now this equation can be represented by this equivalent circuit. So IC n plus 1 is a capacitance current, IC n plus 1 current at the n plus 1th instant, that is entering the p node. From our previous figure, this was the original figure. This current is IC, this node is P, this node is Q. Current is entering pth node and it is leaving qth node. So this can be replaced by, from the pth node, current IC n plus 1 is entering, and that is equal to Gc into Vp minus Vq. So this is like a voltage into conductance or voltage by resistance form. So this first term, this first term can be replaced by this conductance Gc. So if you look at the expression for current through this Gc, you can directly see that it is nothing but Gc into voltage across Gc, that is Vp minus Vq. So we will get this term. So this voltage is Vp n plus 1, this voltage is Vq n plus 1. So there is one more term with a negative sign. There is one more term with a negative sign here. So that term is represented by IC0. Since there is a negative sign, the orientation is given like this, opposite to IC n plus 1. Okay. So this will be the equivalent circuit of the capacitor. So the equivalent circuit I will redraw again. If you have a capacitance like this, the voltage Vc and current IC marked like this, then you can directly replace this capacitance by a conductance Gc parallel with a current source IC0 with the same, between the same nodes. If this is P and this will also be P and Q, where Gc is nothing but, what is Gc? Gc is nothing but C by H. From here you can see that Gc is nothing but C by H. And what is IC0? IC0 is nothing but this quantity Gc into Vpn minus Vqn. Now we will try to use this result in an example. Suppose we have an electric circuit like this and we want to solve do a transient analysis. Suppose we are trying to write the modified nodal analysis equations for doing the transient analysis. Then in here you have three nodes. This is node 1, node 2 and node 3. So we have three variables v1, v2 and v3, and since there is an independent voltage source, current through that independent voltage source is also a variable. So we have four variables, three node voltage and one current is. Now we can write four equations. Now instead of writing the equations one by one, we can easily write it by replacing the capacitance by its equivalent circuit. So this C1 is now replaced by its equivalent circuit GC1 parallel with the current source directed in this fashion. Similarly, C2 is replaced by its equivalent circuit GC2, conductance GC2 parallel with another current source IC02. So this is now an ordinary circuit consisting of only resistors, voltage sources and current sources. Now we can easily write the modified nodal analysis equations for this equivalent circuit. So this coefficient matrix will have four parts: G, B, C, D. This we have studied in the beginning, and this right hand side will have two parts. So what is the G matrix? Conductance matrix. It will be filled like this. The first row, first column element will be the sum of the conductances connected to the first node. So this is the first node. So the conductance only GC1 is connected to first node. So GC1 will appear here. Now between first node and second node, this is second node. First node and second node, GC1 is connected. So second entry will be minus GC1. Then between first node and third node, nothing is connected. There is no direct connection between first node and third node, so that element is 0. Now the second diagonal entry will be sum of the conductances connected to second node, that is GC1 plus G1 plus G2. G1 is 1 by R1, G2 is 1 by R2. Similarly, second row, third column element will be negative of this R2, reciprocal of R2 minus G2. So this we have seen before in the beginning of the course. So like this we can fill the G matrix, and this independent source Vs is connected between node 1 and ground. So in this here there will be an entry of 1. Positive terminal is connected to node 1, so there will be plus 1. Negative terminal is connected to ground, so the other entries are zeros, and the transpose of this will appear here 1 0 0. And since there are no dependent sources, this D matrix will be 0. And the right hand side, how to write the right hand side? Consider node 1. In node 1, the independent current source coming to node 1 is IC01. So the first entry will be IC01. Now consider node 2. The independent current source coming into node 2 is minus IC01. Since IC01 is flowing away, it is minus IC01. Now consider node 3. The independent current source coming into node 3 is IC02. So that entry will come here. Then the last entry will be the independent voltage source in the circuit Vs. So we got the equation. From this you can these equations can be solved. This Vs we have to substitute at the value corresponding to t equal to Tn plus 1. And this can be solved to get V1 n plus 1, V2 n plus 1, V3 n plus 1 and Is n plus 1. So this is how we can use equivalent circuit approach to solve a circuit involving capacitances. Now we can consider a circuit involving inductances. So before that, let us consider a general case. An inductor connected between node P and node Q. The value of the inductance is L. Current flowing through the inductance is IL. So the voltage across the inductance is VL. VL will be related to IL using this famous equation. VL is equal to L into DIL by dt. So DIL by dt is 1 by L VL. Now DIL by dt can be written as IL n plus 1 minus IL n divided by H. And the right hand side is replaced by its value at n plus 1 instant. This is from backward Euler method. Now if you do some rearrangement, you can write IL n plus 1 is equal to IL n plus this H by L into VL n plus 1. So IL n plus 1 is equal to IL n plus 1 is equal to IL n plus H by L into VL n plus 1. So H by L can be thought of as a conductance GL. So GL into VLN plus 1 plus this IL n is IL0. This will be equal to IL n plus 1. So this is the equivalent circuit of the inductor. So and if you have an inductor in a circuit, you can replace that inductor by this equivalent circuit, where the value of GL will be H by L, and IL0 is nothing but ILN, the inductor current in the previous iteration or previous time step. Okay, so if you have any circuit with an inductance, for example, if you have a buck converter like this, and if you want to solve the circuit for the switch on state of the switch, during on state the circuit will be like this. The switch will be on, diode will be off, and if you want to write the equations corresponding to on state, you can just replace this inductance by its equivalent circuit. The other parts remains the same. For the switch, if there will be an on state resistance, so we can model the switch by its on state resistance Rs. Then the inductance between this node P and node Q is shown by an equivalent conductance GL parallel with a current source IL0. And for this capacitance, we have another equivalent circuit that we saw before. So this capacitance can be replaced by its equivalent circuit GC parallel with the current source IC0. Okay, so there is a resistance parallel. So this is the overall equivalent circuit. You can easily write the modified nodal analysis equations for this circuit. So this is how we can do transient analysis for circuits using equivalent circuit approach. Thank you.